In this brief module, we will be talking about a very useful rule in calculus called the L'Hopital rule. It's written in a complicated French manner as shown below. So L'Hopital rules concerns functions when it's not obvious as to what the limit might be. Let's take an example before we state the exact rule. Let's consider a function given by f of x is equal to e to the power x divided by x squared. And let's say we are interested in calculating the limit of this function as x tends to infinity. What's the value of this function? So if you try to calculate it directly, you will see that the numerator goes to infinity, e to the power infinity, and the denominator also goes to infinity, which is what is called an indeterminate number, infinity divided by infinity. We don't know how to calculate it. Another example is f of x is equal to x squared plus x minus 6 divided by x squared minus 4. For this one, if you had to calculate the limit of this function at x tends to 2, you would again get that this is going to be 2 squared plus 2 minus 6 by 2 squared minus 4. So 4 plus 2 minus 6, which is 0. And this is also 0. And this once again is indeterminate. So how do we calculate these limits? Do they exist? If you were to actually go and plot this function, you will see that the limit does in fact exist. So for functions such as these, or in general, L'Hopital rule states that given two functions, f of x and g of x on the same domain, the limit of f of x divided by g of x as x tends to some value c will be the same as the limit of f prime of x divided by g prime of x as x tends to c. So instead of calculating the limit for the ratio of the functions, you could differentiate both of them and then calculate the limiting value of the function. And this you could do if limit x tends to c f of x is equal to limit x tends to c g of x is equal to 0 or infinity. All these bizarre cases like we saw above, this rule would work. So let's apply it to example 1. In example 1, we will now get limit x tends to infinity, derivative of e to the power x, which is same as e to the power x, divided by 2x. So it's not done yet because as you can see, we still have infinity by infinity problem. But L'Hopital rule still applies to these two functions as well. So we can differentiate it once more. And now e to the power x will again stay e to the power x, but the denominator will become 2. And suddenly we have gotten rid of the infinity by infinity problem. We don't have infinity in the denominator. We have infinity here, and here the limit is 2. So the limit for this function is infinity. So you might say, what did we gain between what we had up here and what we have down here? The point is that this is an actual limit. This went to infinity, while on top over here, it was ill-defined. Let's look at example 2. For example 2, we can again differentiate, and now it will be limit x tends to 2. The numerator will be 2x plus 1, and the denominator will be 2x. Now, if you put in the value of x is equal to 2 on top and bottom, you will see this is limit x tends to 2, and this becomes 5 divided by 4, or equal to 5 by 4. So the limit for this function is indeed 5 by 4. So this is a cute little rule, and it is quite useful in a variety of contexts in terms of Taylor series and other things where we have to calculate the limit of a function at a certain point. And at first glance, it looks like the limit does not exist. But under very generic conditions, and I did not go into the eligibility rules for when this rule would be matter, all would be applicable, but what I can say, it's quite generically applicable. I invite you to go and look up the page on Wikipedia to look for the exact conditions, but if you didn't look that up and just used it, as long as these things are happening, circled in blue, then I think you're okay. That brings us to the end of this brief module. Thank you very much.